Good morning, everyone. I'm very happy to be here this morning to introduce the third and last day of the Europe's Rail Innovation Days 2022. So we've had a very good number of technical sessions displaying all the different aspects of the work of Shift2Rail so far. And today we will be having more very interesting sessions. One of them on the theme of rail freight, which is obviously one of our very important topic contributing to the objectives of the Green Deal of decarbonizing transport in Europe. And we will have a second session this afternoon on traffic management. My name is Catherine Cesco. I'm the Chief Stakeholder Relation and Dissemination at Europe's Rail for those who haven't followed the other days. Later on in the day, you will have a very interesting last session with our Executive Director, Carlo Borghini, who will, together with our Head of Program, Giorgio Travaini, look at the outcomes of these three very interesting and intense days on Shift2Rail, innovative solutions. I would like to remind you as well that a feedback survey is available already on our website for you to give your opinion on how we can improve and make these innovation days even more interesting for next year. And you will now be introduced to our first session on rail freight by Manuel Alarcón. Have a good day.
Good morning, everybody. My name is Manuel Alarcón. I am the IP5 Program Manager, and welcome to this freight session of today. A bit of housekeeping before we start. First of all, to ensure a smooth session and avoid any technical difficulties, we have disabled the microphones and the cameras of all participants. But of course, we want to hear your thoughts and your questions, so please write any question or comment in the chat function. The questions will be addressed, and we will have time after each presentation to share this question and answers. Please note that the sessions are recorded and will be available on Europe's Rail website in upcoming days. To be able to join the next session, you simply have to visit the Europe's Rail website and click on the Join link in the Innovation Days program. Please be aware that each session has a different link. Please do not come back to the current link to attend other sessions. So for us, this means that for joining the IP2 session, you need to go and click on the link you've got for this afternoon, starting at 1:30. Okay. We would like also to invite you to comment on how we can improve our events in the future. A dedicated survey will be made available on our website as of Friday, 9th of December afternoon. Please do not hesitate to take part. Finally, you are also invited to subscribe to our mailing list by visiting our website. Like this, you will receive the final takeaways of the event, including the survey and the recordings. So having said so, if I can go to the introduction. And next slide, please. Okay. Here we are. Basically, I'm going to give a very, very brief introduction for all of us here. And for those that are not acquainted to the program, IP5 is the original Shift2Rail innovation program specific for freight. It has unfolded its activity through different projects. Today, we are looking at Freight Rail 3, that somehow is the continuation of the Freight Rail series. It is a very important project as it gets close to the end of the program, so we can see how the innovation reaches quite an interesting maturity status. And it is quite a very interesting project in the sense that we've got the best of breed in freight, I think, doing innovation here. And we are reaching quite interesting conclusions and challenging horizons. No? Today, we've got quite a condensed schedule, but nevertheless, I think we are going to make it somehow interesting and enjoyable for all of you. And I would like to introduce Dr. Patrick Sees. He is the he's the project coordinator for Freight Rail 3. He is he works for Deutsche Bank Cargo, and I pass on the floor to him. Good morning, Patrick.
Good morning, Manuel, and thanks a lot for your words. So, hello everyone, my name is Patrick Seesle. I am the head of the Europe's Rail Innovation Program at DB Cargo and the coordinator for the Freight Rail 3 project. I am the successor of Norbert Karl, who is the overall coordinator of the IP5 Shift-to-Rail community, and I will give you a brief introduction to our today's final event for Freight Rail 3. We are very happy to present today the results from very good engineers, data scientists, and researchers from this rail freight communities. The goals of the Freight Rail 3 project were to make the rail freight system more efficient through the usage of data such as intelligent video gates and different sensoric devices, but also a lot of other very interesting and good comprehensive results from this project. What is very interesting today that we are also going to address with a lot of topics, the reducing of energy consumption, which is very important nowadays. Some are directly with a more efficient use of energy, and some are indirect with the more efficient use of our rail freight assets. The Freight Rail 3 project is with this result addressing a lot of topics from the common IP5 vision, which was created back in 2016 when all the work here started. And with this, we are also have achieved a lot of goals addressed within the Shift-to-Rail Master Plan and also in the multi-annual action plan. As already mentioned, Freight Rail 3 is part of this whole IP5 project family and builds up on projects like Freight Hub, ARC, Freight Rail, or Freight Rail 2. Some of these topics will end within this project, like, for example, the work package 2 regarding the real-time network management. And others are going to be finalized within the project Freight Rail 3, Freight Rail 4 in the next year. We will present now, within the next 3 hours, the results from 6 work packages that have been developed within the last year. The first one is condition-based maintenance. Here we are developed on the basis of multiple use cases, several user-centric dashboards to really see what issues are at the moment with the assets and how we can bring these assets automatically or semi-automatically into our maintenance processes. We also already presented some of these results on the InnoTrans this year. The second work package is regarding the real-time network management. Here we will see today an interesting demonstration of a yard management software, which was demonstrated within the Malmö yard. The third one is regarding the intelligent video gates. Here the work was focused within Freight Rail 3 on the process of the installation of intelligent video gates in Sweden and also in Germany. And it was one of our biggest challenges during this project to get these installed during the COVID pandemic. But at the end, everything went well, and now these intelligent video gates are running and really improving the rail freight system. The next one is the extended market wagon. And this is one of our very good examples of good collaboration development within Shift2Rail, and one of our biggest highlights of this year's activities. It was very challenging to finalize this prototype for this year's InnoTrans, and we were all very, very happy when we received the message that everything is finalized and is going to ship to InnoTrans. The specification of this wagon was also made within this project, Freight Rail 3. The next one is telematics and electrification. Within this work package, we have very exciting results and developments, and also very interesting and good field tests this year in our DB Cargo yard in Minden. The last work package, and also one of our most interesting ones for today, is the freight loco of the future. Battery-powered locomotives are crucial nowadays for a more sustainable future in rail freight, and is also covered within this Freight Rail 3 project. So it is really worthwhile to stay connected until the end. And as already mentioned from Manuel, you are not able to unmute or switch on your camera. We will have dedicated question and answer sessions after every work package. So if you have a question, raise your hand or drop your question into the chat. Please understand that we might not able to address all questions today, but we will come back to you via email or other ways if there's something you're interested in and you want to learn more or want to know more about. Also, my inbox is always open, so if you have after this final event further questions, please contact me directly. Now I will hand over the presentation to Karina Schmidt-Klaassen, one of my very esteemed colleagues. And I would say, Karina, the stage is yours.
Thank you, Patrick. So now we, Annalena Peitz, me, Karina Schmidt-Klaassen from Deutsche Bahn, will show you what has been achieved within Work Package 1 condition-based maintenance of RedRail 3. Before we start, let me say some words. After more than 1 year as a work package leader in CBM, it is a pleasure for me to hand over my responsibility in this program to Annalena. In the future, Annalena will be the new work package 1 leader. Next slide, please. Before we go into our results of work package 1, I want to show you the objectives of our part. This objectives on the slide was defined at the beginning of RedRail 3. Generally, we have dealt with the following 3 main topics: use cases itself, CBM architecture, and the European focus. First of all, we wanted to improve the existing use cases and identify new ones. Secondly, we wanted to create an advanced monitoring based on existing data and experience. Another big goal was scaling. And thirdly, it is the European level. We wanted to apply existing use cases to other European fleets so that synergies can be created. In order to achieve our goals, the work package was divided into 5 tasks. Next slide, please. These 5 tasks can be mapped to parts of the CBM architecture on the right side. The CBM architecture was developed within RedRail 1. Task 1.1, 1.2, and one part of 1.3 focused on the locomotive use cases. The other part of task 1.3 dealt with the wagon sensors. The task 1.5 focused on wayside monitoring. The live monitoring was covered by task 1.4. Now I will hand over to my colleague Annalena Peitz. Thank you.
Karina, good morning. Seems that you're muted.
Yeah, good morning, Manuel. So Annalena, can you
Hello, everybody.
Oh,
Can you hear me? Yes?
Yes, we can hear you.
Wonderful. Thank you, Karina, for the short introduction. Now I can show you what CBM actually means. So can you switch the slides? Thank you. Condition-based maintenance changes the maintenance process by using information about the equipment as the driving force. The aim is to turn interval-based maintenance into condition-based maintenance so that an unplanned component failure as shown in the picture above can be avoided. Can you go further, please? Thank you. So the aim is to turn interval-based maintenance into condition-based maintenance so unplanned component failure as shown in the picture above can be avoided. The typical maintenance is based on time intervals or is kilometer driven, so inspection is only planned in workshops. This leads to the fact that an unexpected component failure results in higher cost and a negative impact on the availability. CBM solves this problem by monitoring components and systems, so potential failure can be predicted and the locomotive will only maintained when necessary. What are the advantages? We can increase the availability and reduce the maintenance costs by 10%. In Shift to Rail, we have identified about 40 use cases. For example, a use case which dealing with the battery voltage, but we also focus on use cases which are dealing with the energy consumption as well. After this short explanation of CBM, I can show you which impact condition-based maintenance has at DB Cargo. Today, 8 train engineers are working together with 9 data specialists to analyze new use cases. Also, 6 IoT device manufacturers and 4 IoT platforms are involved. With 1,600 equipped lockers, we collect 150 gigabytes of data daily. This results in over 60 million signals and 1.5 million messages that are processed. With this data input, we currently create over 100 specific damage codes. Next slide, please. Now let's have a look in the results of task 1.1. The scope of task 1.1 was to see if already applied use cases in freight rail 1 and 2 could be scaled to other locomotives in other countries. Within the different fleets of DB Cargo, locomotives in Poland and France were examined. This, of course, does not mean that the use cases are only applicable to DB Cargo. In theory, interested railway companies can easily adapt these use cases for their own fleets and implement them as well. In total, 28 use cases with the possibility for upscaling were identified. The scheme we use to identify these use cases is shown on the right side. 2 conditions must be fulfilled. The first question was, is the required data accessible? And secondly, we answered the question if the use cases are capable to optimize the current maintenance program. If also the second box could be ticked as fulfilled, the use cases is deemed to be an interest of the corresponding locomotive. Next slide, please. While task 1.1 deals with the existing use cases, task 1.2 was dealing with new ideas and possibilities. For this analyzed, we used the funnel method shown in the picture. First things first, the ideas are collected and then the possible use cases are evaluated in different stages to see if they are financially and technically feasible. If so, the next stage is to describe a solution on how the use cases is to be monitored in reality. For this, a solution concept is defined. After defining a solution concept, the validation phase is started, and if necessary, a prototype is tested. And then the fleet rollout can be prepared. And after preparation, the use cases is implemented in the fleet and set live. Next slide, please. So, what did we achieve with this method at DB Cargo? More than 1,100 maintenance alarms were triggered by algorithm based on IoT data. As I mentioned before, we identified about 40 use cases, and now you can see the automation status of these use cases. So 31 use cases are live and send their alarms to a dashboard. And here we need an engineer to analyze the data and steer them into the maintenance depot. We also created 2 semi-automated use cases, which must be verified by an asset engineer and then pushed into the ERP system. And last but not least, we also created 6 fully automated use cases, which send their issues alerts directly into the ERP system and no asset engineer are involved. Next slide, please. So now we will show you the work and results of the other task. In task 1.3.1, a sensor system for the use cases are being developed for a locomotive regarding the oil monitoring from the Research Institute Act. And in task 1.3.2, the Research Institute site analyzed the helical springs on a freight wagon. And in task 1.5, I will summarize the activities regarding the wayside monitoring, which is an interesting technology to monitor entire trains without having to install sensors to each locomotive and wagon. And now the following slides will be presented by Christoph Schneidhofer.
Yeah, hello from my side. So, yeah, thanks for the introduction. Yeah, my name is Christoph Schneidhofer from AC2T, located in Austria. And I now present you the results from the task 1.3.2 regarding CBN of transformers in electric locos. So please, next slide. Yeah, to enable CBN, we need on the one side the proper sensors and on the other side the proper algorithm for the data interpretation. And therefore we divided our work in this task as is shown in this slide. So we have the aim of the work located on the top row. And therefore, using our lab to field approach, we were able to move the development from a low TRL level 1 to TRL 5 within this project. Starting from the system analysis to identify the most critical oil parameters. Then based on this, we select the proper sensor system able to analyze these critical parameters. And the most work in this project was related to the validation of this system using our laboratory environment to validate the system in relevant environments. And finally, the field test was prepared together with Deutsche Bahn, and the main execution of this is then planned within the next project, Freight Rail 4. Please, next slide. Here, some words about the system analysis and the sensor compilation. So here, the work was based on analysis reports, which we received from Deutsche Bahn. And thereout, the water content, the electric loss factor, and dissolved gases were identified as the critical parameters. And therefore, we researched the proper sensor system. Next slide, please. Here, some words about the proof of concept. Using the sensors, we developed the sensor development environment to test the sensors under close to reality conditions. So here we build up an oil circulation system where the oil gets in contact with the sensor system. And this we combined with an artificial aging to simulate the critical oil degradation mechanism. Here we focus on the one side, the fundamental functionality of the system. And for the oil degradation mechanism, we simulated influence of water, a fault condition by arcs to simulate dielectric faults in the transformer, and also thermal oxidative degradation we apply to simulate the buildup of acids in the transformer oil. Next slide, please. Here on this slide, we see the result of the laboratory validation. So here we clearly demonstrated that the system are able to identify the individual degradation mechanism, starting from water content was identified by the relative humidity sensor. Arcs in the transformer, for example, can be nicely detected by an increase of dissolved gases, for example, hydrogen. And the buildup of acids was nicely shown by the oil condition sensor. And all these results were implemented in the algorithm to detect these degradation mechanism. So next slide, please. So concluding, the sensor system is appropriate for this application, and we can detect water content, oxidation, and hydrogen within the sensor system. And using the algorithm which we developed and the defined thresholds, we can enable condition-based maintenance for electric locos. And finally, we developed the demonstrator together with Deutsche Bahn, where we want to implement the sensor to the electric locos to demonstrate also the system working in the field. Here I want to thank Deutsche Bahn for the good cooperation in this task, and I'm looking forward to execute then the demonstrator within the next project, Freight Rail 4. So thanks from my side, and I want to hand over to the next presenter.
Thank you very much, Christoph. Good morning, everyone. My name is Unai Alvarado. I am working for CEIT, which is a technology center located in Basque Country, north of Spain. And we have been working in Freight Rail 3 in the monitoring of helical springs in the suspension elements of freight wagons. So the starting point was initiated in the previous project, Freight Hub, because DB was experiencing some problems with the suspension elements and lack of knowledge about the deterioration of springs. They only monitor the static stiffness of the spring in the workshop when major revision is happening with the wagons where the bogies are disassembled. Also, we took as a starting point the Innovac project, which made an analysis of the criticity of the different components of freight bogies, and we saw that in them the helical springs were a critical component, not in terms of how costly they are in terms of maintenance, but their impact in safety. So our goal was to monitor helical springs with low-cost sensor to detect degradation. Next slide, please. Then we developed a monitoring system that was composed by two sensors at both sides of the spring pair in this case. And we applied as an algorithm and a frequency transformation and FRF to detect the amplitude and damping factor of the natural frequencies of the spring pair, and this way try to early detect any changing in the condition of the springs. So we did a lab validation with springs in different health conditions, and then we moved to tests in the field. So you see there some tests that we did in the past. We installed the sensors in different spring pairs in different wagons. Unfortunately, we were not able to cover degraded springs. So the springs in the one hand were new, and in the other wagon were not very degraded, not new, but like semi-new. And these are the results that we got. Next slide, please. As you see there, raw data on the upper left. We did several runs back and forth, and some curious stuff were happening. You can see on the upper side of the slides, the two graphs there are raw accelerations, and we observe very strange thing happening and sort of amplification of the accelerations. And this is mainly due to one element in the spring pair that was a Lenoir link, a frictioner that was there, that was amplifying the signals. So this was not a good effect. So we have to focus on spring pairs that don't have this element. On the lower part, we have new springs and old springs, and you have the FRF. And the first conclusion that we have is that the information is not very clear there, as we observed in the laboratory. The natural modes are present. We can see something at the 100 Hertz mark, but not very clear tendencies are observed. If you go to the next slide, please. Yes, these are different responses on the second test runs that we had. You see how the response loaded versus unloaded is there, and the new springs with semi-new springs. Some similar responses are observed up to 100 kilohertz, but from then on, the two graphs go apart from each other. The only good thing that we observed is that these results, where the two springs are operated together, are very similar to the one that we observed in the lab. And last slide, please. We then went to carry out a new set of tests, because we thought that the higher natural frequencies were not being excited. So this is why we tried to do a new run. Unfortunately, in this new run, we were not able to work with degraded springs, because for sure for safety reasons. And we did the tests in Marcelin yards up to 25 kilometers per hour, and going through different switch and crossings so that higher frequencies might be eventually excited. This is a new graph that is plotting the time frequency analysis of the FRF. You can see on the left-hand side the excitation and the response of the upper spring, and on the right-hand side the FRF. This is for new condition spring, and if you go to the next slide, this is for degraded springs. Main conclusion is that not very clear tendency, unfortunately, is observed due to the running conditions. So next slide. As a conclusion, we did the testing in this condition up to 25 kilometers per hour, and with a few switches and crossings, in order to excite the response of the springs in higher frequencies, and use two sets of different springs in two wagons, new and semi-new. Unfortunately, we couldn't use degraded springs to observe more clearer tendencies, but the target frequencies were not excited, and not clear repeatable patterns were observed. So new approaches, considering the holistic system, the whole wagon, or eventually the whole boogie interacting with the track, will be explored in next projects within Europe's Rail. Also, as Christophe, I wanted to thank very much to our colleagues in DB, especially Patrick and Fabian and Malte, for their support and help during the preparation and the execution of the test. Thank you very much.
So as I mentioned before, wayside monitoring is based on sensor system installed along the trackside. This offers the possibility to monitor certain components without having to install sensors and telematic devices onto the train itself. And the main goal of this task is to examine the possibility of moving from an existing reactive approach to a more proactive approach for wayside monitoring. And in a first step, the existing infrastructure developed in Sweden by Trafikverket and Germany by DB was analyzed in detail. And in a second step, it was investigated how the infrastructure already in place could be used to transition towards a CBM approach. And the third part was to examine alternative systems that are available on the market but not yet in use of DB Cargo or Trafikverket. And finally, gaps to be filled within available wayside monitoring systems and AI were examined. The results of this task we are used in a follow-up task in Freight Bill 4. So next slide, please. The final task from WP1 we will show you is the CBM dashboards. And a general problem when handling big amounts of data is the processing of it. In task 1.4, a set of dashboards has been developed with the goal to standardize and automate the visualization of the use cases. And they have been developed in close collaboration with future users and are designed in a way that they are easy to adapt to all kinds of use cases. Next slide, please. On this dashboard, the battery of a locomotive is being monitored, and the voltage of the battery is measured, and the results are visualized here in different graphs. And a big issue of batteries are deep discharges, which can shorten the lifetime of a battery significantly. And with the data we collected, a quality value is determined and plotted on the right side. And if the quality value of the reaches a threshold, the battery must be exchanged. And more than 40 of such dashboards has been prepared so far, and a set of dashboards is growing with a number of new and future use cases. So next slide, please. These were our results of work package 1. Do you have any questions for us?
So thanks, Annalena, for this very good presentation. There's one question in the chat. Are the use cases transferable to other European Union fleets? Perhaps you can answer it for our European fleets.
Yes, of course, all use cases can be leveraged, but operationally, behavior may differ.
Okay, so we have a generic approach. So for the setup, for the definition of the use cases, but then really in the operational use, it depends on sensoric devices and what log types they're using, etc. Something like in this direction?
Exactly, yes.
Okay, perfect. Are there any other questions? You can drop it in the chat. You can also raise your hand. The easiest way is the chat. I will give you another few seconds to think about. Otherwise, thanks a lot to the whole team for condition-based maintenance. We have seen some works are done here within Freightware 3. Other will continue within the Freightware 4 project, where the final event will then take place probably somewhere mid to end of next year. And if there are any questions, please get in contact with us directly via email, via LinkedIn, and I can moderate these questions to the dedicated experts. Now I would like to hand over to Magnus Warburg and Sarah for the work package 2, real-time network management. Very good to have you here, Magnus, and please, the stage is yours.
Thank you, Patrick. Can you hear me well?
We can hear you very good.
Perfect. So I will have this presentation, real-time network management, together with Sarah. And I will start with some background, because this is shift-to-rail yard and network management. And then we will go into this with cooperative planning and what we have done at Malmö yard. And we will also have a demonstration that will be number 3. And then at the end, we will have this with a workshop conclusion and next steps. Please, next. We started this September or October 2016, and then we have been working with this yard and network management. And we started with many projects and a wide approach involving many countries. It was Sweden, Germany, but also more countries as Czech and Italy. And then at the last part, we have been focusing on demonstration in Sweden, and this with Trafikverket, RISE and Indra. So next, please. When we started this in the first project, ARC, we were looking at the different actors with the infrastructure manager, yard manager, and freight rail operators. And we also started at the biggest yard in Sweden, in Hallsberg. And what we understand is that there is a need to share information between the inbound, outbound yard and the marshalling part, and also then to connect to the network. And we identified a number of problems, and by this improved information sharing and improved communication possibilities, we can solve problems. Next, please. So what we understand is that this is a general problem, and we also developed this with sending yard, network, and receiving yard. And in this presentation today, we will describe the demonstrator that we have developed in Malmö yard. And Malmö is, compared to Hallsberg, a much more bottleneck. And we have 3 yards. We have a common arrival departure yard, connected to a terminal operator, and then also connecting to a marshalling part. And then we have then also connections to the network, to Denmark, Germany, and to the network in Sweden, Southern Main Line. Next, please. What me and Sarah shows today is this with this demonstrator at the Malmö yard. But in the project, we also have had activities from KTH. They have been developing machine learning forecast of yard departure times, and to combine with simulation for forecast arrival times. And also Linköping University have made research in optimization of trains when disturbances. But today we focus on this coordination system and yard coordination system. Next. And you can take next. So now we will come into this concept. So the rules, we have our research partner, RISE, and they are working then with the requirements and specification, and also have had this dialogue with the users. And then we have had the system supplier, Indra, developing this demonstrator. And then the problem owner is Trafikverket. So Trafikverket then is the line manager and also in control of this arrival departure yard. And then Trafikverket needs to improve communication with the yard manager, Green Cargo, and the terminal manager, MERTS. We also have, of course, the freight rail undertakings, but the main focus have been this with Trafikverket, Green Cargo, and MERTS. Next, please. And you can have a next one as well. So this picture shows the Malmö yard. So we have this common arrival departure yard where the freight train pass and is this shared resorts. And then we have MERTS multimodal combi terminal, and we have this marshalling part. And also these then needs to have this to go the train via the arrival departure yard. Next, please. So the background and purpose then is that we have developed this demonstrator to have this improved communication and between Trafikverket, Green Cargo, and MERTS. And especially during time, this is a critical resource, and it is then a bottleneck. And today we have a real lack of information sharing. And what we are developing is this with proactive planning. And by this proactive planning, then we improve the communication between the actors. We improve how we share information between the actors, and especially also the line planning and the yard planning. And by this, we also establish an increase in transparency. So these demonstrator makes then rail freight transports to be more competitive and more effective. And by this proactive nodes, we can also enable smoother traffic and also reduce energy savings and also more punctual traffic we see. Next, please. And here I will hand over to Sara.
Yes, so hello everybody, my name is Sara. And what we want to show with this picture is that what currently happens is that whenever a driver wants to go to the arrival or departure yard, they call the line manager and say that they want to move into the arrival departure yard now. So there is no planning, and the line manager don't really know what's going to happen during the next few hours. So next slide. And that is what we want to change. So we want to have a system where the terminal manager and the yard manager can share their plan and tell the line manager what they intend to do, and where the line manager then can coordinate all these different actions and make sure that we don't end up having operational conflicts, but rather can solve them before they become a reality. So this little square that is now connected to all the actors is the YCS, the yard coordination system. And next slide. And that is the research prototype for shared planning that we developed during this project. So it is a web-based tool for demonstration. It is not intended to be an operational planning system ready to be used right now. And nope, keep the last slide. And you can log into it with 3 different roles. You can be a yard manager or a terminal manager. And they can obviously see the plan, but they can also communicate their needs and communicate what they plan to do. And then you also have a line manager role that can see the plan, obviously, but also can make these track reservations on the arrival and departure yard. And that is because it is the line manager's responsibility and right to actually allocate track capacity on the yard. So it is a difference in these in roles between those actors. You can obviously see the plan and any outstanding planning tasks, and you can also see conflicts, where conflicts are, for example, when you have 2 trains being planned on the same track at the same time. And these conflicts are identified based on a set of rules that we have developed together with the actors. And now we can go to the next slide. Because what I'm going to do now is that I'm going to show you a little bit about how this system actually works. So this is the YCS when you have logged on, and you have the tracks on the y-axis and the time on the x-axis. And little arrows represent departures and little T's represent arrivals. And you can see that we have some frames, yellow frames, and that means that I have a planning task that is outstanding. Right now, I am the line manager, and all these yellow frames basically means that I have not put in any initial plan for the trains. So I can just do that by putting in the default values that have been identified. So it goes quite quickly. And now you're going to see that we get a conflict because now we have 2 track allocations overlapping. And then to solve that, I can simply just move the train to a new track. I'm still going to get a conflict here because this train moves to the south and these 2 tracks are not really connected in a good way for southern departures. So then I have to keep working to find a good solution. There is still a conflict, but I can see on this train that's already standing on track 4 that this red little box, that is the requirement sent in from the marshalling yard manager that says that I'm only going to use this track for this amount of time. So then I can actually change the track allocation reservation to only cover the time that is actually needed and my conflict is solved. So that is the type of things that we want them to be able to use this tool for. And if I instead move and go to the yard manager view, you're going to see that some trains are less visible. That's because these trains are not relevant for the yard manager or for the classification work that they are going to do. But you can also see that I can change, for example, I might not want to start working with this train 5317 until I'm done with 5613. Well, that's pretty much done already. Okay, I can start working right away, but then it's not going to take an hour, it's only going to take half an hour. So then I can change my how long I am going to need this track, and it is going to be visible for the line manager so he can change his plan. I can also say that I need a track for some shunting operations. And it pops up and it's also visible for the line manager who can then say that that is fine, if it is fine. So that was basically what I was going to show you. So we can go back to the meeting and I can stop sharing. And we did test this tool in a workshop with the actors. So next slide, please. And then we had participants from Trafikverket, so the infrastructure manager or the line manager, and also from Green Cargo, who is the current yard manager, and Mertz, who are the current terminal manager. And the questions that we asked was, would this kind of tool be useful? And also, are there any important features that are missing? So next slide, please. And in this workshop, we used the YCS with the 3 different roles, so logins. And for some of the scenarios, we put the participants in different rooms and used phone for communication to sort of mimic the current practice. And we also had an Excel document and a game leader to represent the reality in time. So time moved forward at a normal speed, unless everybody were bored and had nothing to do, then we could fast forward time. And trains arrived and departed with variation that mimics the current variations that we have in Sweden. And we also had the game leader calling the line manager and asking for permission to drive to and from parking spots and to and from different tracks and so on, to sort of have the same type of working load that they currently are used to. We tested 4 different scenarios. The first was just an introduction scenario to get everybody used to the YCS and to the working with the Excel document. And then we had a normal day, so trains arriving both early and late, with a variation that is standard for Sweden. Then there was a snowy day when we had to close down all of the tracks but from 2 for snow removal, and also a bridge closure, which meant that the bridge to Denmark was closed, so there could be no trains departing towards Denmark and Germany. And that obviously affects the yard in quite a major way. Next slide, please. And the conclusions were that a tool like the YCS would be very useful. However, the data entry needs to be easier or better automated, because it's quite hard to handle at the moment. And there is also, we think that there might be a challenge to move from this sort of reactive behavior where you do something when somebody calls you, to thinking about the next few hours and actually do this proactive planning. And we noticed that sometimes nobody really knew who was going to take command and make sure that the plan was changed when there were things happening. So it is going to be a change that needs to be managed in a good way. And the nice thing was that all of the participants saw lots of development possibilities, and they sort of like thought of this as a first step towards a more digitalized yard management. And they were also very excited and wanted to start using this, for example, in more pilots during the weekends where the researcher could sit next to them, to sort of get their hands on it and start trying it out, rather than having to wait for years for the final perfect system to be implemented. So they were very keen to work with these types of tools. And now I'm going to hand over to Magnus again.
Yes, so so this is the next step that Trafikverket, we will continue development of this YCS in Europe's rail. And what we are planning for is integration with the surrounding systems like TMS and other important data sources. And we are also will develop planning functionality and enhancement in this demonstrator. And also this will be done in FA1, but we also will have integration with FA5 about this collaborative decision-making concept. So it will have one leg in FA1 and one leg in FA5. And Malmö node will be the demonstration site. So we will proceed with the users and the organization that we have started cooperation with. And that was the last slide for us.
Thanks a lot, Magnus. So, are there any questions regarding the demonstration? Here is something in the chat. At Sarah, how close is the demonstration system to be in use as an operational tool? So, yeah, I think the question is clear. So how is it in operational use at the moment, or used within an operational tool?
Yeah, it is currently not used as an operational tool. It was developed as a research prototype. I would say that the functionalities in the specification, they are quite mature, but then to actually have an operational tool, you need a different kind of development and support. during using as well. So
is there
yeah.
planned something regarding this? So for the exploitation within Europe's rail to further develop.
Yes, we will proceed in Europe's rail. So that's
clear.
the plan. Absolutely.
Okay, so then this is some work that will end with the Freightway 3 project. The question is, so how you look back at all the work from the last year? So what was the highlight from this collaboration work within the real-time network management tool?
For me, I think anyway, for myself and in Sweden, that we have learned a lot during these years, and we are working with building up knowledge. And at Trafikverket, we are currently looking at all our yards and in some way to have a strategy for the future. And also this with the different rules are of interest, I would say.
Yeah, to really integrate it into the processes. Very interesting. There are another 2 questions in the chat. I would start, I think, with the easier one. In which of the flagship areas you will going to continue your work? I think you already addressed it, but please repeat it for answering this question.
Yes, we will address it in FA1, but then we also will connect to FA5 because we will have some information sharing from FA5. But
Very good.
The main focus will be real-time network management and also our current TMS.
Okay, then second question from Philip, perhaps a little bit more in detail. Do you plan to consider integration with TAF TSI?
I mean, we have looked at the TAF TSI messages when we developed it, so we understand that the estimated arrival time message and could be good input, and the estimated departure time message is obviously an output that we could improve the quality of. But I don't think we have decided how we're actually going to connect the different data sources yet.
Okay, thanks a lot. So we would have a little bit more time for questions, if there are any. Otherwise, let's go. Thanks a lot for your presentation. And we are going now to the topic of intelligent video gate. And we have Besat with us. Besat is the dedicated expert for all intelligent video gates, works within Ship2Rail, also Europe's Rail. And Besat, the stage is yours.
Thank you. Good morning to you all. So my name is Besat Kornejad. I'm a researcher at KTH, Royal Institute of Technology in Stockholm, Sweden. And we are a linked-in party to Swedish Transport Administration, Trafikverket, who is leading this work package. Together with partners from Indra, Hitachi, and DB. And Trafikverket also has research institutes, RISE and Learning Well as linked-in parties. So this slide shows the overall structure of our work package, which we call Intelligent Video Gate. So this work is a continuation of our work we did in Freight Hub project, where we looked at these kind of gates usage on terminals, intermodal terminals mainly. But here we also have included shunting yards. And we actually managed to install a gate in Gothenburg. And we have also have a gate in Nuremberg for yard purposes. So the second deliverable here dealt with the demonstration or description of a demonstrator. So we looked mainly for AI machine learning tools for image processing. This task was led by Indra. And we also have looked at data sharing possibilities and exploitation possibilities. And this task has been led by RISE. And this final deliverable here today, we will describe the most considered use cases which we have evaluated. And we will talk about this mainly during today's presentation. We have made several dissemination activities, a video I will show you soon, and papers presented at WCRR and Nordic Railway Seminar, for instance. Next slide, please. So this figure shows you an overall concept of the gate and the technologies used. So the technologies used are mainly OCR through video. So this optical code recognition is then used by image analysis and machine learning models, which, as I said, our partner Indra has developed. Complementary technologies, RFID. So the wagons equipped with RFID tags, they can be read by RFID readers connected to these gates. You can also mention sensors is also a technology used here. So the sensors activates the illuminators when the train comes and also measures the velocity of the train and the wagons and can adapt the cameras to it. The data sharing possibilities, for that we have developed a platform which we call Deployed. And this development work has been led by Rice. So these technologies then can detect, identify useful information, wagon codes, sequence in the train, intermodal loading units codes, and thus also the sequence within the train. So there are different type of numbers and codes which we'll read. And another aspect is danger goods placards and also damage detection. So these are the things that we have been looking at. And having this kind of information, operators at yards and terminals, and also the infrastructure manager can improve processes, handling, for instance, with deviation for check-in and check-outs, improve the transshipment for a yard or for terminals, and have a better interface toward road haulers. And I will talk more about these useful aspects in the use cases later on in the presentation. Next slide, please. So as I mentioned, we managed to build this gate in Gothenburg. Although there was a pandemic and travel restrictions, our partners, mainly this task were led by Hitachi, who traveled to Stockholm, and we also managed to build this gate then. As you can see to the figure to the left, the gate here has two cameras on the sides of the train, and also we have the RFID reader just in front of the wagon there. And as I mentioned before, there are sensors connected to this gate in order to activate the illuminators and measure the velocity. And this gate is positioned roughly 10 minutes from the port of Gothenburg, which is the biggest port in Scandinavia. And within that port, there are several terminal operators then who could use this information for improving the processes. Next slide, please. And the gate in Nuremberg, Germany, this is connected to a yard there. And just by the hump, the shunting hump, we have this gate. And this is mainly used for maintenance purposes. And as you can see, there's also cameras from above here that can also take pictures from above. Next slide, please. And here we see a demo for a wagon going through this gate in the yard of Nuremberg. And you can see also the corresponding images that it takes. We will talk about later on about the use cases for yard purposes. Next slide, please. And here we have a video.
Shift to Rail is the first European rail initiative to seek focused research and innovation and market-driven solutions. To take us one step closer to the modern and more competitive railway, an intelligent video gate, an IVG, has been developed within the program. The train runs through the gate, and the gate can collect data with the help of camera images and optical readers supplemented with information from barcode scanners. By implementing the IVG, automated and digitized real-time information can be created for several operations that today take place manually. The gate can detect wagon numbers and unit numbers, train composition, identification of dangerous goods placards and UN number, as well as detection of wagon damage. This information can then be used in management systems at terminals and data sharing with stakeholders in the multimodal chain. The project Freight Rail 3 within Shifter Rail demonstrates and analyzes functionalities for 2 intelligent video gates, one in Nürnberg in Germany and one in Gothenburg in Sweden. The one in Germany focuses on identification of damages, and the one in Sweden focuses on data sharing between actors. The IVG in Nürnberg is located by the shunting yard. The focus is to train an AI program that can identify wagon damage automatically. This process will enable an improved damage management of wagons and load carriers, as well as a more efficient use of shunting yard, as the damaged wagon is automatically identified by the IVG. Another IVG was built during 2021, here between Gothenburg Port and Kville Railway Yard. The test with the IVG here in Gothenburg will focus on intermodal freight transport between the railway and the port. To enable useful functionalities, the interface has been developed to analyze the information received from the gate. Automated and digitized processes in the intermodal freight transport contribute to increased utility and quality. For example, by improving management of deviations, increasing quality of information and information security, optimizing transshipment, contributing to more precise times of departure, increasing the operational efficiency, and enabling information sharing between concerned actors. By building an intelligent video gate here in Gothenburg, we can gather experience that can lead to greater development with more gates and increased data sharing between stakeholders.
Okay. So great. Thanks to Closer and for helping us to produce this video. Just to make a short clarification, there are then RFID readers and OCR, which are the main technologies in the gates here. Okay, so we move on to the use cases, which we have identified and evaluated here. The first use case here was led by Research Institute RISE, which called it information to the customer. So the customers of the railway undertakings and terminal operators specifically can get up-to-date information about the goods, have a better understanding where the current locations are of the loading units, wagons, and the trains, and get a more precise estimated time of arrivals. And this information, the timestamp information, can be compared to the already pre-advised planned information in the timetable and can be presented to the customers or the end users of this information in a user interface. Next slide, please. So this is the user interface which we developed to this model called Deployed, thanks to RISE then. And this shows right now the location of the gate in Gothenburg and the type of information that can be retrieved by users, where the wagons and loading units are positioned, if there are any RFID tag codes detected, and so on. Okay, next slide, please. Next use case, also developed and led mainly by RISE. So here we consider the planning aspects for the terminals specifically, and the transshipment, that is the movement of the loading units on and off the trains or the wagons. So having a more precise, up-to-date reading and sequence of the wagons, they can start to plan and optimize their processes for transshipment in a better way. So then the movements can be reduced and you can have a reduced energy consumptions. Having a better planning in the terminals also provides a better connection to road hauliers. So trucks can come and go when they're supposed to do, and by that we can also reduce energy consumption. So the gate in Gothenburg currently, based on our current analysis, thanks to Indra, they have correctly identified roughly 80% of the wagons, 85% of the loading units. And here we are not looking at damage caused. Damage here we define as graffiti, which I will talk about a little bit later. So this hit rates we believe can be increased if you do some further work with investigating why they're not identified. Main reasons for that are national codes. There are loading units which are, for instance, here Swedish codes and not international standardized codes. And there are also administrative reasons, such as wagons, multiple wagons having only one code. So we can move on and work further on increasing these hit rates. Thanks. So this slide then shows the camera or the video gates in Gothenburg having two pictures from the side. You can then, if there is a code that's not detected, you can detect it from the other side. And you have a better damage detection options here as well. So you can see here we identified ILU codes, wagon type code, and the dangerous goods placards. Next slide, please. So concerning the damages, the main damage that are considered here in this part of the project is graffiti. And the deep learning model that Indra has developed currently achieves a more than 98% detection of graffiti. So we are quite satisfied with the hit rates here, as this is the main source of code reading failures actually. Further studies need to be done to automatically detect other type of damages, such as corrosion, bumps, structural damages, and ground cable disconnections. Next slide, please. As I mentioned, dangerous good placards are also very interesting to be able to automatically detect and identify, not only for yard and terminal operators, but infrastructure managers need to keep a good track of these units. And currently we identify around 70% for the dangerous goods. So we believe that this hit rate can be increased if we use, for instance, matrix cameras with color. So then these colored dangerous goods placards are more easily detected. Next slide, please. Perhaps I forgot to mention that the previous use case was mainly developed by Indra, the dangerous goods use case. In this other use case, we're looking at dangerous goods and the interconnection to the traffic management system. And this use case was developed by Hitachi Rail together with Trafikverket. So we made a case study here to see where these gates should be positioned in order to give input for the traffic managers for a certain line. In this case, the line is considered between Gothenburg and Malmö Central, or Malmö Yard actually, which are the second and third largest cities in Sweden. So here we try to investigate what are the best options to have this kind of gates along this line in order to recognize the dangerous goods and give traffic planners options how to reroute, for instance, in the case of an accident. This should be viable, useful information. Next slide, please. So through the model or the patent that it's actually developed here, you can see that it tries to optimize or minimize the consequences of us in case of a rail accident. So we should know how the number of people that could be exposed to this type of dangerous goods and calculate the minimum when the risk is minimized. during the day, certain times of the day, or which places they could be more exposed. And here we have said, for instance, Varberg and Halmstad along the line. These are good positions to have these gates. Okay, next slide, please. So the final use case is actually several use cases at yards, which we are considering. So the use case at yards, the marshalling yards, are mainly connected to maintenance diagnostics. So instead of sending, for instance, wagons to a wagon workshop, you can detect the maintenance issues by the cameras and have savings, for instance, for wagon workshop operations. You can use this for damage detection, increase the undetected damages, and by that reduce the cost for damage claims and customer-induced damages. And also having a better maintenance operations, you can reduce the needs of external maintenance service providers. So next slide, please. So to conclude, we believe that the IVG concept has showed very good potential in automation and digitalization of rail freight transport chains in terms of reducing time and speed up the technical checks for departure and arrivals at nodes. And the main technologies here, the use of image processing together with machine learning model have proved to be very good. And we have also showed that we can share the data, exploit the data along the supply chain. However, we believe there are further improvements regarding these aspects of image processing and data sharing. We aim to have hit rates above 95% to get us like a good stable system and provide stability. And to do that, we think that we need to be able to recognize more code types, such as national code types as well. And in order to share the data in a secure and efficient way, if you would have a larger set of networks of gates, we need to have the common format for data sharing, semantic aspects of data sharing. And these are actually aspects that we will work further on within EU Rail and IP5 there. The work which we call standardized European checkpoint at borders and other operational stops. So with that, I would like to conclude my presentation. Thank you.
Thanks a lot, Behzad. So there are many questions in the chat. First, I would like to address that the video that you have seen are also posted in the chat. So if you want to use this video for another presentation or want to look at it again, the chat is in the chat. The first question is, are there already some camera bridges used in the production? So do you have yeah, that's the first one. Used in the production. So are there in operational use these camera bridges?
Yes. So what we showed, the gate in Gothenburg is in operation, and also DB has, as we showed, also the gate in Nuremberg, but more cameras are installed and will be installed as well for DB's part. And for Trafikverket, we plan to build at least 2 more gates in Sweden. And I know within the FP5, as I mentioned, the continuation work there, more camera bridges or gates, as we like to call them, will be developed.
Exactly. So the right term, intelligent video gates, were used within here, Shift2Rail Europe's Rail. And the question is, do you have a rollout plan? I think this is then more addressing so in the direction of Trafikverket and DB.
Yes, definitely. And yes, there are considered the rollout plans, I know, from the infrastructure managers and when and how to set them out. But I think the next step here will be also, as I mentioned during the presentation, have a cross-border functionalities to look at gates on borders and have a better interoperable system along the borders.
And this is focused in the work of FP5.
Definitely, yes.
Okay, then one question from Carl. What need is there for wagon and load data detection, which is a tough TSI requirement anyway? In columns wagon list of every train and should be available long before the actual arrival of the train. Data quality provided, of course. You can also see it in the chat if you want to read it again, Peter.
Yeah, but there is a very good question related to the tough TSI, and we believe that more elaborated collaboration or connection to that can be done, obviously. But we think that this type of data may be changed along the route, like the sequence of the wagons and the intermodal loading units may change. And this is not the only information we get from the gates, the sequence of the units, damage detection, as we mentioned, the dangerous goods placards. So there are more aspects involved here that can be retrieved from tough TSI, I would say.
Okay, I hope this will answer the question, Carl, but if not, please get in contact with us and we can clarify this. The next one are, how long does it take to train an AI on one wagon type to detect damage?
On one wagon, how long? Yeah, this question should be addressed, I think, to our partners from Indra, who's been responsible for this AI aspect. But for one wagon type, I don't think that would be a main problem. They have lots of wagon types included in the model. The question is also what type of damages we are considering. Some damage types are more difficult than the others. This we know. So that's what we have started with graffiti, which is quite a clear type of damage and also improves the detection rates and the hit rates for the wagons and the loading units.
Okay. Then from Johannes, one question, what is default rate? I think we have seen it.
Default rates?
Default rate. So I think how many errors do we have? That's something going to detect it, which is not damaged. I think this is in this direction.
That was a little bit difficult to understand, but so if they're not damaged, what's the default for that? Yeah, that's a little bit tricky to understand.
Okay, so we will come back to this. Johannes, I can contact you afterwards. And then there are two bigger questions. I need to take a look on the time. Okay, we still have time. First, to identify wagons and cargos, including hazmat hazards, why are you focusing on using image processing and not relying on using RFID, which is cheap, reliable, and insensitive to dirt, graffiti, etc.?
Yes, good point. A good question from Hans there. I would say that one aspect is that RFID is a complementary system as we see it, because not all wagons are equipped with RFID tags, and loading units, for instance, many of them do not have RFID tag. So yes, we need these kind of cameras to be able to capture that. And yeah, that would be the short answer, I would say.
Okay, perfect. So then the final question, also a little bit bigger one. You can also see it in the chat, Besat, using image processing. Why are you not focusing more on detecting mechanical conditions and faults, such as brake shoe thickness, wheel rim thickness, etc.? I will call it like this.
Yeah, more use cases and more functionalities can be actually added to these gates. So, for instance, if you would like to automate some aspects of the outgoing trains, for instance, the automatic brake test or such things, there can be worked on and to improve this as well. But I would also say that the gates, mainly at the yards, these are used for maintenance activities and can detect some of these aspects which are mentioned.
Yeah, I think we are also going to much more detail regarding this question than in the final event for Freight 4. We have more this technical use cases. So thanks a lot, Wesat. I'm also a big fan of this work with intelligent video gates, and it's also a very good example for collaborative work within Europe here together in the rail freight community. Yeah, then I would say with a quick watch on the time, let's go over to the extended market wagon with a presentation of Dr. Roland Bench and Maxime Weidner from Contraffic. And then afterwards, we will have a quick break that everybody can fill up their coffee mugs, etc. Dr. Roland Bench, Maxime, the stage is yours.
So
Maxime is
good.
here. Perfect.
So thank you very much, Patrick, for the introduction. Unfortunately, Dr. Roland Bench is not available today. He is in another project meeting, so his apologies, but best wishes to the community. So my name is Maxime Weidner, and I will introduce the work of Work Package 4, which is dealing with the extended market wagon. So I'm working for Contraffic, which is one of 4 partners in the Competitive Freight Wagon Consortium, CFW. The other partners are the DLR side and the German Railway Industry Association, Verband der Bahnindustrie in Deutschland. So we are dealing with the so-called extended market wagon, EMW, and the key objectives for this work package here in Freight 3 was on the one hand to finalize the specification for realizing a prototype of the extended market wagon. So when we started in Shift to Rail, our goal or our aim was that we in the end of Shift to Rail, that we can present a full-scale prototype of a completely highly automated flat wagon. So that is the one point. The other tasks were system integration of all components and relevant subsystems in all the relevant dimensions. So that means in the dimension of mechanical integration, but also as we want to achieve a highly automated system, also in the electrical design. And last but not least, as we consider this research projects not as a pure development or research project, we were also thinking about the market uptake or market launch of such a system, and therefore it was necessary to think about the approval concept, and that was also done within Work Package 4. Next slide, please. Just to give you an idea where we came from. So Freight Rail 3 for us is one of the projects out of a row of 5 projects. We started with Freight Rail 1, which were mainly dealing with business analytics, so analyzing logistic change, the transport market, identifying relevant markets, and the potential for shifting transport volume from road to rail. And these were absolutely necessary inputs for the then following projects, the more solution-oriented projects such as Freight Rail 2 and Freight Rail 3. In Freight Rail 2, we dealt with wagon concept, running gear concept. We made simulations, multi-body simulation, in order to get a higher maturity level before we then go into the prototyping, which is done in the Freight Rail 4 project. Just to give you an idea how where we stand with Freight Rail 3. And as perhaps not all of you know about the extended market wagon concept overall, we have produced a short animation video where you can see the overall production concept and some functionalities of the intended prototype. So next slide, please, and then you can start this film. So So what we here see is what we call the closed train loop production concept. So we have a dedicated route with dedicated terminals that the train passes. So A, B, C, and there will be other ones. And this is done on a fixed scheduled or fixed timetable basis. So it's comparable to how you today book a train journey. So you know about trains leaving in a starting area, and then you can book your free platform. So we have this flat wagon here with interchangeable containers. We foresee these digital automatic coupling with Type 5 functionality, and we want to fully exploit the maximum length of 750 meters. So with this CFW EMV Type 3, we have 44 wagons. And now the train is running to the next terminal, so fully exploiting 750 meters in single traction. This perhaps what's worth mentioning is that we have a dedicated loco fixed to these wagons. So now it arrives in the next terminal, and then you see the command from the locomotive onboard unit giving the command to the train to go into unloading mode. That means handbrakes and the automatic corner lockings now go into unlock. And so the containers can be picked from this platform. So there we have the air suspended running gear. So with height compensation and ensuring constant spring rates, we assume or we foresee the train running at higher speeds than nowadays, so 140 kilometers per hour. And also equipped with GNSS positioning. So we go into the side view. So see 2-axle wagon aerodynamic fairings and much shorter wagon transitions due to the application of the DAC Type 5. So due to the electronic brake control which we have on board, we have much better longitudinal dynamics. And this is also the reason for that is that we want to go into the daytime with these freight services. Okay, that's perhaps a short introduction of the overall production concept and some features of this new extended market wagon. Next slide, please. So in total, we foresee plan to have 3 wagon types for different needs. So in terms, when it comes to Hafen-Hinterlandverkehr, we foresee the EMW Type 1, which can carry these toys, 20-foot equivalent or 20 feet ISO containers, or if you don't have 2, then 1 40-foot container. And for the realization of the prototype, we focused on Type 3, which is down below, that is can carry these swap body Type C, ranging from 7.15 to 782 meters swap bodies. Next slide, please. So as I said, the overall goal from work package 4 was that we make sure that every single component, either it's a mechanical one or it's an electronical one, can be integrated. We had to define the communication architecture. So we have, starting from the locomotive, we have so the mastermind, so that we have the locomotive on the board unit. That is, as I said, the master of the overall communication system. And we have on each wagon, we have a wagon onboard unit that is monitoring the status of the relevant components, such as level control, the digital automatic coupler, the platform lockings, and of course, the electronic brakes itself. And executes the commands that are sent from the locomotive. And with that, we also defined what you see on the right side here. We defined the processes, so command and control processes for the different functionalities, such as coupling, decoupling, brakes, level control, and so on and so forth. So that was done in the task 4.3, I think it was. Okay, next slide, please. So we have, with that, as we are dealing not only with cargo management relevant data, but also with safety relevant functionalities, we have defined the so-called safe train integrity system, STI. And we also defined or specified how the train configuration process is managed. So and how the wagons are sending their commands to the locos, saying, I'm here, I'm coupled, and then the next one comes, wagon number 2, for example, it says, okay, I'm coupled, I'm here, and so on and so forth until the end of the train. So the configuration process is defined, and all the other functionalities like handbrake functionalities or the electronic or the emergency brake functionality and so on and so forth are specified and defined in this work package 4. So we have here, as you see, the loco onboard unit, the VOBUs, dealing as, well, considered as slaves. And within each VOBU, we have this electronic brake control and also a data processing unit that processes the monitored conditions. And if there are relevant information that are related to kind of safety function, then these data will be transferred to the driver desk. Yeah, so that measures can be taken according to this type of failure, for example. So yeah, here we have the list of all the things we are doing there: lock and unlock the Type 5, the platform lockings, supervising the level control with overload detection, of course, and we have several other sensors foreseen, like temperature sensors of the wheelset bearings, air pressure sensor, and of course vibration sensor monitoring for wear and malfunction and derailment detection. So next slide, please. That was one of the other tasks. So the final wagon specification, so explaining the typology of the extended market wagon on the one hand, but also going into the detail of the architecture and the relevant components and subsystems. So we have chapters dealing with the structural design and the chassis, the running gear is defined, the wheel set, brake disc, and so on. One other topic that you might not find in other projects is the fairings. So the wagon itself is almost fully covered with fairings to optimize the aerodynamic drag, for example. And then we have the other parts dealing with the electrification, sensor network, energy supply, brake system, coupling, and transport platform corner lockings. So that's done within this second deliverable, as you see on the right. Next slide, please. As I think these innovation days have a guiding theme, which is energy saving. We have also some aspects related to that, increasing energy efficiency. At considering comparable train, we expect up to 20% energy savings per train, and this is due mainly to, of course, a lightweight design, as you can see on the left, and this aerodynamic shape that gives more energy efficiency. We can reduce the number of axles because the loading weight is ultimately defined by the permissible total weight of the commercial vehicles on road. And that's why we can reduce the number of axles per wagon to 2. And that gives us more possibilities of lightweight improvement. On the other side, so on the left, on the right side, you can see from the video these wagon transitions. They are much shorter because there are no classic buffer elements foreseen. So we apply this digital automatic coupler type 5. So we don't foresee any manual operations in the decoupling process or in the coupling process. And therefore we can leave this large safety room called Berner Raum. And that's why we can reduce this wagon transition significantly. And that has a huge effect due to, or in terms of aerodynamical drag. You can significantly reduce this drag because you achieve a rather homogeneous overall structure of the train. And that is one of the key points to save energy as well. And besides that, you also have, in terms of economic improvements, you gain a lot of more load capacity per a complete train set. Okay, next slide, please. This is one excellent example, as our work package is more or less a lot of paperwork, but there's one thing that's a typical development project. So as you saw in the video, we foresee these automatic corner lockings because the train is running at higher speeds, up to 140 kilometers per hour. So we need kind of lift-off protection for the swap bodies and containers because we are running at high speeds, or in case of encounter traffic or strong crosswinds. And when we decided to go for such a functionality, we did classical market research and came across this manual solution, which is a solution from the roadside. And there was no other component or solution that we could easily implement into our wagon. So we decided to go with this mechanism and improve the design to make it fully automated and controlled by these wagon onboard units. So that in the middle is one of the design studies, and the one on the right, we did also some prototyping for the Freightrail 4 project then to introduce it and show it at InnoTrans. So that was the one nice story within Work Package 4, that we are not only dealing with paper and defining and specifying components and subsystems, but also go into development and ending with 8 real prototypes for integration into the wagon. Okay, next slide. With this, I want to conclude the presentation of Work Package 4. As we consider the overall research project not as a pure development project, just to show what could be implemented and be developed. We were also thinking about introducing this concept, this wagon, into the market. So there was a need to think about the homologation process and how this can be done with a completely new wagon with different functionalities. So the initial situation is as follows. As you have seen it in the video, we have a fixed mapping between fixed assigned locomotive and a group of wagons. So there is no interoperability need in terms of UIC compatibility. It is fully supervised the train integrity in operation with the CL4 STI system. We have this electronic brake controls there. We have automatic corner lockings and of course the digital automatic coupler type 5. So that's the initial situation, and with that the overall application is different, and there's no need or no requirement to be compatible to the UIC freight system. With that, the UIC specification coming from the leaflets is not relevant for the homologation of such a system. And therefore, the wagon itself is not considered to be the homologation entity. It's the overall train set, so loco together with these wagons. And therefore, we don't see a need for standardization outside this homologation entity and keep the space open for future innovations. Yeah, you can compare it a little bit like modern passenger trains. So the different wagons of an ICE train are not compatible to a regional train or whatever. So within this train formation, this one is what we call the homologation entity, and therefore we can refer to other TSI rules, and that's described in our last deliverable, which is the deliverable 4.3 that is describing the overall approval of the concept for this wagon technology and production concept. Thank you very much.
Thanks, Maxime. So very interesting presentation, and for me it was very exciting which improvements are possible with such an approach and technical innovation. So are there any questions from the community in the chat? Yeah, there is one. Does the shift from 4-axis to 2-axis bring any disadvantages with it? First question.
So yeah, there might be, or what was earlier expected were some instabilities at higher speeds, and these were considered or were simulated in the predecessor project in Freight 2. So we had different variants of this running gear and put it into a multi-body simulation. There we could improve using some other stabilizer elements and could show that there are, in terms of running stability at high speeds, with the final design approach, there are no instabilities. So the multi-body simulation showed that this wagon is stable until almost 200 kilometers per hour.
Okay, thanks a lot. Any further questions? I would have a question, Maxime. So what are the open tasks to finalize the work for the extended market wagon within Freight 4?
Yeah, the open tasks are one milestone was achieved. That was the presentation at InnoTrans 2022. So this autumn, We could show all the functionalities we wanted to show. There are open tasks, so there will be some dynamic test writes just to gather some more data from the real world. So that should be done in the next spring. And while the wagon was produced, manufactured, we also become aware of some integration aspects that could be improved in a pre-series of such a wagon. So there are some points that can be improved, cabling, piping, and so on and so forth. Yeah.
Okay, summarize it to improve some points which you have detected and also to test it in a more reliable environment.
Yes.
Okay, another question in the chat. Do you expect increased rail damage with only 2 axes?
Sorry, didn't get it. So do we expect
increased rail damage with only 2 axes?
Why is that? Oh,
okay, then I would say it's probably
no, we don't expect it. So
yeah.
as we focus on not on the heavy rail-affine goods, but on these so-called low density, high value goods, so that are transported on roads, we don't expect damages to the infrastructure. No, I wouldn't say.
Okay, perfect. So then, any further questions? Otherwise, I would say let's make here a quick break until 11:30.
Yeah.
Manuel, please.
Yes, thank you very much. Fantastic morning so far. We have seen quite interesting activities. We have seen how the different work packages have delivered their action and the final results. So very interesting, especially video gates and also the CVM and of course, you know, the telematics and this extended market wagon. Very interesting questions. And for example, we've got the last one saying, why do you need a DAC5 in the case of fixed wagon sets? And maybe Maxim, you can answer.
So this is, that's a good question. In the beginning, we only foresee at the very end of the wagon set, so one side and the other side. But when we investigated the terminal infrastructure, we started with Germany, we saw that you don't have the flow through principle in terminals mostly. So you have one entrance, and through that entrance you have to pull out the train again. And you have limited track length in terminals. And that's why you have to make sure that you can decouple also in the operation mode. So you feed in the 750-meter train into the first track, and perhaps it's only 360 meters long. Then you have to decouple. Then you have to decouple between wagon 22 and 23, for example, and then you pull out the train, the rest of the train, and feed it into the second track. And that's why we foresee DSC type 5 at every second wagon. So we have a set of 2 wagons fixed coupled, and at the end of these sets you have always DAC type 5, so that you can feed into the different track length of terminals.
Okay, thank you very much for the answer. So as we were saying, I think it's time for a little break. So I would say let's go and grab a coffee, a bit of a beer break, and we see each other in this same place in 10 minutes time, and let's see if we can steal a bit of time to the schedule, and we can arrive to the end even with a bit of time to have a bit of a recap or washing up on it. Okay, so let's go for a small coffee break, 10 minutes, and we see each other at 11:35. Okay, I'm going to leave it in the chat, so if somebody is maybe not listening or whatever, knows what is happening. So okay. So, hello again. I hope you have had a fantastic break. And now we carry on with our plan. I can see my very good friends, Heisky and Stefania, and they're going to talk about something which I believe is very interesting. Moreover, I think it's a very challenging topic and a quite how I say, a very interesting innovation for freight rail. So I think it's time for freight rail to get into telematics and electrification and so on and so forth. And they come with very interesting proposals. So with no delay, I pass on the floor, first of all, to Heisky. And Heisky, the floor is yours.
Thank you, Manuel. So may I present directly, or there will be someone moving the slides?
Well, somebody will be moving the slides, and the idea is, yes, please do present yourself.
Okay, thank you, Manuel. So let's start. This is Jaizki Mendizabal from CEIT Research Center in North Spain, and I'm leading here the freight wagon smart concepts, where this telematics and electrification is included. So what we are going to present today is linked to this smart freight wagon concepts. You already saw just in the previous session this standard market wagon presented by Mr. Weidner. This is part of these concepts where we also had telematics and electrification. This is not an isolated activity. In the freight rail series, we've been working with it. But in this case, for freight rail 3, we brought the high energy brakes for freight, which will be presented by Stefania. And yeah, we can also say that freight rail 3 will be the last project for this concept. So we will have end results. And then I will present telematics and electrification, focusing mainly on onboard positioning and power harvesting, where you'll see what is the results we've obtained in the final field test. So said that, as mentioned, first energy brakes for freight, then telematics and electrification, and I will give the floor to Stefania to present the activity of the brakes. Thank you, Stefania.
Thank you, Aiski. As Aiski mentioned, my name is Stefania Ferrara. I work for the company Fevere Transport Bochum, and I'm the task leader for the task 5.3 related to the development of a new brake disc for freight application. The concept development of work for this new brake disc started within the scope of the project Freight Rail 2, as you can see in this slide, in the work package 1, and continued then within the project Freight Rail 3, work package 5, telematic and electrification. And thanks also to the prototype, the disk prototype and testing in a lab environment, dynamometer, we were able to reach a TRL 4 after this project. Next slide, please. So let me explain you which was the main target of the development of a new brake disc for freight application and which way we chose in order to reach this target. The main development target was actually clearly energy saving, and we chose to develop one single brake disc per axle in order to reach this target. Nowadays, as you can see in this picture, brake blocks brake directly on wheels or two brake discs per axle are common for freight application. We want, our idea was to substitute the two brake discs per axle with one single brake disc. This would result in a strong reduction of the weight of the vehicle because you have just one brake station with one disc, one caliper, and one part for the brake system. And consequently, we have a strong reduction of the energy consumption of the vehicle. And furthermore, because we have one brake station less, we can reach a strong reduction also of time and cost for maintenance and a reduction of the supply costs. Next slide, please. So in this slide, I just show a scheme of the different steps necessary for the development of the new brake for freight vehicles. I will go into detail for every step in the next slides. Thank you. The first point, important point for the development was the design of the disc. We decided to abandon the traditional commercial concept of a cast brake disc, and we introduced an innovative design based on a new welding technology. As you can see in the picture, the disc is not a cast disc, it's not a unity, but it's made out of different components which are manufactured, assembled, pressed and welded together. And at the end, we have, after the welding process, the wall disc. The disc is made out of two different friction rings. You can notice in the picture the geometry, the targeted geometry of the disc with this very distributed thin on the disc surface, which enhance the thermal capacity of the disc. And in order to connect the friction rings, so we have a series of balls and lugs, which have different functions. First of all, they act as the spacers for the brake disc. They are also responsible for the cooling of the disc, and they are necessary for the assembly of the disc to the hub. Next slide, please. Another important point for the development process was the material selection. Because we applied a welding technology, we had a very high flexibility in the selection of the different materials for the different parts of the disc. We decided to use steels, so with high characteristic, high mechanical properties for the plates, which are necessary for the manufacturing of the friction rings, and for the bars that you can see in this picture, which are necessary for the manufacturing of bolts and lugs. Next slide, please. Parallel to the design and to the material selection for this new brake disc, we carried out also brake calculation and a thermal simulation of the disc. You can see in the picture the model for the FM simulation and so some example for the result of the thermal simulation. What I want to underline with this slide is that the thermal simulation of the disc was a crucial point for this development because we are substituting two discs to brake disc per axle with one brake disc per axle, and that means that the braking energy that traditionally spread in two brake discs will be considered just for one brake disc. So this brake disc should be able to manage with a very high amount of braking energy. That's why it's also called high energy brake for freight application. And it should be able to dissipate this high amount of energy, which is transformed during braking in thermal energy. So the brake disc should be able to dissipate a very high amount of heat as energy. Next slide, please. So after the concept development, we manufactured the prototype by showing this video some step. Here's the manufacturing of the friction rings. It's laser cut, the drilling in the friction rings. We carried out also a very accurate control of the dimension. And now the components are assembled. They are pressed to each other in order to manufacture the disc. In this position should be the disc welded, but this is not shown in this video. And now we have the last steps related to the last machining steps of the disc and last dimensional control of the disc. So once that we concluded manufacturing of this innovative brake disc, the last step of this development was the test in a lab environment at an anemometer. Next slide, please. So we compiled a targeted test specification with a wide series of brake application under different conditions, wet condition, dry conditions, different conditions of speed, of clamping force, and initial temperature by braking. We made tests with a route profile, and we also uses the EU regulation TSI for freight wagon, which includes a very challenging drag braking, which simulates the Gotthard route with drag braking with a 21% slope. During this drag braking, the disc will see an energy amount of 45 kilowatt for, if I remember well, 34 minutes. So it's a very high amount of energy for one disc. Yeah, during this trap braking, the thermal capacity of the disc is real tested. You can see in the picture the disc assemblies at the anemometer. You can recognize also the geometry which we developed in order to improve the thermal capacity of the disc, to improve its cooling performance. You can see also 3 motivated engineers ready for measurement at the anemometer. Next slide, please. So I wanted to show with this video, not our disc, this is a general braking process. What happens during a braking of a disc is that the braking energy which is applied at the disc is transformed in thermal energy. You can see the brake caliper giving clamping through the clamping force, this braking energy at the disc, and is immediately transformed into thermal energy. The disc can reach very high temperature. In this case, you can see that the disc is incandescent, so the temperature can rise level of 700 or 800 degrees. If the disc is not able to dissipate this high amount of heat, of energy in form of heat, then this temperature can damage the disc and its safety is not anymore guaranteed. So what happened to our disc is that through the dynamometer test, we reach a too high temperature on the friction surface and on the disc, which has been developed during the drag braking related to the regulation TSI for freight wagon. That means that we were not able anymore to guarantee the safety of the new brake disc. And that we realized that it was necessary a further investigation in order to improve, to enhance the thermal capacity of the disc and its performance, its cooling performance, in order to dissipate a higher amount of energy. For this reason, we do not have any follow-up activities in the following project of Freight Rail 4. So I'm at the end of my presentation. Thank you for your attention. Eski, I give you the floor for your presentation about telematics and electrification.
Thank you, Stefania. Yeah, when we move now to telematics and electrification, as other activities in Shift2Rail, this has been spread in different projects, Freight series projects. And as you see here, we had a number of projects. Now we're focusing on freight rail 3, and the main target are the main demonstrators in freight rail 4, focusing on the core market wagon, extended market wagon, which both of them have some telematics in it, and the telematics and electrification specifically. So if we can move to the next slide. Great, thank you. So from this Freighter series, we identified a number of use cases for that telematics and electrification could cover. These use cases, again, are not isolated, are linked also to other IP5 shift-to-rail activities. So, for example, use case number 1 relates to continuous condition monitoring. This is mainly linked to condition-based maintenance that was presented this morning by Corina and team. We also have the automatic coupler, use case 2. I should mention that this intelligent wagon, the core of the telematics, is the element we called the wagon onboard unit. So the wagon onboard unit has the intelligence to connect to a number of devices into the wagon, and also to connect to other wagons and the locomotive through the intra-train communication, and it might also have capabilities to connect to the track side, depending on the case. So this wagon onboard unit would be responsible for command this automatic coupler type 5. Then we also have use case 3 related to cargo monitoring system to monitor the cargo. Use case 4 was defined for the onboard positioning. So this is one of the services the intelligent wagon will offer. Onboard train integrity is also a use case. And finally, the wayside onboard monitoring data integration. We have some references to wayside monitoring from our condition-based maintenance team, but there is also, we have also explored the possibility of exchanging information gathered on board with the information which is gathered wayside. All these are offering and require a number of services which are also enablers. Here we listed 14 of them, where I will highlight this train integrity control, which also covers train composition, train length, data processing, which is mainly key for wagon monitoring. And we have a number of different sensors approaches to monitor brakes, loads, suspensions, axle bearing, vehicle to track interaction. We saw some examples in the first session of the day. And just let me highlight also positioning and power harvesting, since these are the two of the services enablers we have been focusing in this project. So if we move to the next slide, we are going to see how the focus is mainly in this project on the wayside onboard monitoring data integration, on the onboard positioning, and also on the power harvesting. I would like to highlight here that the services enablers listed before are not specific for a given use case, but they are distributed among all these use cases. And in this Freighter 3 project, we have been dealing with these specific topics, while in previous projects, other elements, subsystems, enablers have been developed. So if we move to the next slide, we are going to see some information with regards to positioning and speed. So we have worked in different aspects. One of them was the analysis of the devices that have been already installed on wagons. So more than 60,000 wagons have been analyzed, where a telematic device to provide the position is installed. And we have seen that more than 90% of those devices have been working properly. So this means, among others, that telematics can be installed on these freight wagons, and we could provide further functionalities to the freight wagons. Even though it is a tough environment, electronics can work there. Another analysis we have been doing is using sensors for other applications with to obtain position and speed. In this case, we had the axle box accelerometers, and we have been analyzing whether this information, apart from the status of the wheel set, rail, we could also obtain position and speed, and this analysis have been done. And yeah, finally, what we've done is based on a wagon onboard unit, we've included a number of sensors to obtain the onboard positioning. In this case, we're using GNSS, GPS, and Galileo. IMUs, inertial measurement units, and ultra wideband. And with these three sensors, we aim at increasing the accuracy and the availability of the onboard positioning. So here, thanks. If we move to the next slide, please. Thanks to the telematics team, and especially thanks to our colleagues from DB Cargo, we have been able to carry out field tests in the Minden terminal, as you see here in the picture. Our main conclusions are that GNSS is really useful for open sky, as we expected, and accuracies of ±2 meters have been reached. Then for IMUs, IMUs could cover short GNSS shortages and increase the output rate. And finally, ultra wideband is really suitable for indoor or to locations where a higher accuracy is required. As you see there, we had accuracies of 30 centimeters. And main work here, apart from the performance of each of these sensors, have been analyzing also the transitions. So how the system behaves when transiting from using only GNSS to using both of the sensors, or just moving to ultra wideband exclusively. So this work has been done, and this helped us to obtain all these conclusions. Now, if we move to the next slide, we'll see the power harvester. Okay, at the end of the day, we need some energy for all this intelligence, for all these devices. Can we obtain energy from the axle when the train is moving? And the device showed here is aiming at doing this. Okay, the requirements for this are having a speed equal or higher than 20 kilometers per hour, and we might create an output power between 20 or 120 watts, depending on the speed, with an output voltage of 24-48 volts DC. All this will be stored on a battery that could supply the energy to the electronics. And one of the main characteristics and requirements for this device was the easiness of the installation. So this device currently is quite easy to install, and it will provide the energy to those wagons that are not wired and have no energy in there. So in the next slide, we are going to see the full process. So we started with some electromagnetic simulations, calculus, and so on, so to obtain how the engine of the system should be. Then we also worked on the mechanical part of the system and end up in a laboratory test bench. So in the picture of the middle, you see the laboratory test bench. And finally, we installed it again in Minden in another field test at that terminal with the support of our colleagues from DB Cargo. This system has been presented also at InnoTrans, as you see in the video on the left-hand side. This is the test bench that was connected to the oscilloscope, and you can see that whenever the system starts rotating in the oscilloscope, we can see a signal. I would also highlight that this power harvester is modular. So we could either include a couple of them or manufacture it bigger to obtain more power if needed. Okay, this is just the first prototype that shows that the engine itself is working properly. And on the video on the right-hand side, you can see how it was tested on field, on the Minden terminal. And our main conclusions were that the engine of the power harvester is generating the energy we expected for the speeds. And depending on the wagon, the installation needs to be adapted. I mean, there is some engineering requirements for installing the harvester to have the mechanical fixed section required, and also to bring the cabling to connect it to the battery wherever the batteries will be installed on the wagon. So if we move to the next slide now. Okay, so these were just some of the developments we have done during Shift to Rail for this telematics of the smart freight wagon concepts. And what it will come, and actually what it is coming, is the 3 main demos for this part of the work into Shift to Rail. And in Freight Rail 4, the core market wagon demo with its own telematics. The extended market wagon demo as presented by Maxit Weidma with the telematics, and also some telematic specific demonstrators for the use cases I listed before, and the services and enablers are being carried out, and this will come all latest in 2023. So thank you.
Thanks a lot, Jaski. I think when we quick jump back to the previous slide, we see there was a lot of work within this year with the presentation at the InnoTrans, and also the 2 different field tests. And I think we could learn a lot from each other, and it was very good to work and collaborate together with you. So are there any questions from the community? Perhaps something in the chat? There's something for Stefania. Which kind of material did you use for the brake disc?
Yes. Usually for brake disc for freight application, cast iron is the most common used material because of cheap material, and it's a very, very good thermal behavior. But we could not use this material because of the high thermal stress on the disc, and so we use different grade of steel. So we use a special steel for the friction rings, which showed very high wear resistance and high strength at high temperature, and high strength against fatigue at high temperature. And also we use another steel grade for the bolts and the lugs to be connected with the friction ring. Also, this second steel had a very good strength at high temperature.
Thanks a lot. So there are 2 more questions. We need to a little bit take the time. The first one is from Lisa. Also for you, Stefania, was rail noise a concern at this stage in the project? In columns, does this new disc brake produce more or less rail noise when braking?
Yes, exactly. Actually, brake disc, they produce much less noise than the common brake blocks on wheels. So it was also an advantage which can be considered for the development of one single brake disc per axle, but it was not the main focus of the development, because we focus our research on the thermal capacity of the disc. This was a secondary, very important advantage, but not the focus of the development.
Not the focus in this stage. Okay, thanks a lot. And then there's a question from Philippe. Is there a continuation of the development of telematics use cases services also foreseen in the Europe's Rail program?
Yeah,
like train composition, train integrity, and positioning.
Thank you. Thank you, Patrick. Thank you, Philip. Yeah, I can confirm that we didn't cover completely all the use cases, and therefore there is some work still left. I can also say that the focus now for this freight is coming in the digital automatic coupler. So even though we have been working with being independent from the digital automatic coupler, these applications will be also needed to be developed in trains, in freight trains, where the digital automatic coupler is included. So the answer is definitively yes. So there will be still some further work on telematics to cover these use cases and to adapt the systems to what will come in the future.
Okay, thanks a lot. So then I would close the question and answer session and would like to hand over to my colleagues from Alstom and HVL, to Andrzej Rickerman and Alice Polic, about the freight loco of the future.
Thank you, Patrick. Thank you, Stefania.
Okay, hello everybody, and thank you, Patrick, for the handover. So let's come to the first slide, please. So we had several tasks to fulfill and to investigate. So first one is to improve the auxiliary network on a locomotive to minimize the losses. So it's about energy saving. We looked also at the volume and the weight, and the overall topic was to use medium frequency control and 6 semiconductors. Second topic is about design of a highly efficient, no, stay on the same slide, please. A highly efficient traction system to minimize converter losses, again, about energy savings. Both result in a small scale prototypes, and we have a second bigger topic with battery modules for locomotive that will be presented by my colleague Alice Polic. Next, please. So about the auxiliary network, what did we do? So we replaced a standard auxiliary converter, which is typically fed out of the DC link of a traction converter, using standard frequency output of 50 Hertz, three-phase, including very big, heavy transformer output filters. So, and we replaced this with a medium frequency converter, or DC-DC inverter, and with an output stage for inverter for three-phase again. Working with a switching frequency of 35 kilohertz on this medium frequency transformer in between. And with that, we could reduce the weight about more than 50%, volume more than 60%, and the efficiency increase is about 16%. That results in an overall average energy saving of 22,000 kilowatt hours per 100,000 kilometers. And if we consider price, investment is of course also a very important topic for the industry. So we, due to the quite volatile electricity price, we took two assumptions. One is based on 15 cents per kilowatt hour. The second assumption on 25 euro per kilowatt hour. And we see that the amortization is quite far away, between 17 and even up to, if the energy cost is lower, up to 30, more than 30 years. So why is it anyway interesting? Beside of the very low return of invest or long time, it could be very interesting if we look on the weight and volume savings. So because especially in a locomotive, weight and space is often a very big constraint. If we cannot save it here, we need to save it somewhere else, and that also results in a very high cost increase in the end. Okay, next one. So the second topic, we looked on optimized motor inverter. And what did we optimize? We increased the dV/dt, means so the voltage increase, and we also used silicon carbide semiconductors for this. You see on the left-hand side our famous Trax locomotive, spread over all Europe. So, and we considered four different design variants. The first one is a standard classic single silicium IGBT module. Second one, the silicium IGBT dual module. And then for step 3 and 4, we used the new HVM modules, we call it high voltage modules, with silicon carbide MOSFETs. And why is it twice the same? One is cost optimized at the bottom. That means anyway, we have to switch them or to connect them in parallel. And of course, there you have certain tolerances and to choose either to put 2 or 3 or even 4 in parallel or even one less. So that's then what we investigated as well. So we use different reference tracks mix for the overall simulation. And we do it in 3 steps. First one is just to replace the silicium by silicon carbide semiconductors, no other changes. Second, to optimize the switching patterns, because SiC allows much higher switching frequencies. And the third step is also looking on the whole system. So we also optimized the overall traction chain components, magnetic components, etc. Next, please. So here you see the results. On the table on the left, I don't go in all the details, but we simulated all the different design variants in these 3 mentioned steps. And what we discovered, we started with 100% of the traction converter losses in the first white column. We could decrease the pure converter losses, important to mention, down to 30%. But with all the optimization, increasing switching frequency, which also caused a little bit additional losses, and optimizing the magnetics. So we ended up at the optimum overall system approach at 45% of the total, and that results in approximately 2% of energy savings on the whole traction chain. So looking all again on the commercial aspect, so today it's quite similar with the auxiliary. We had a return of invest between this 70 up to 30 years. And we would need a cost decrease by 40 to 50% to come down with a return of invest to approximately 5 years. So meaning 2% energy savings on the traction system level is achievable with SiC semiconductors. But if not, the weight and space are important, so we still expect and need a further price reduction. Next one, please. So the next step still to perform is that we build small-scale prototypes. On top, you see a schematic for the MF DC-DC with an AC output stage. And filter components that will be built in Zurich in our power lab. Same as for the second one, you see the schematics for the motor inverter part. You see an example of the high voltage module of the SiC for 6.5 kilovolt. And due to the overall crisis and COVID on all the delays we had, so we are here a little bit delayed, and I'm happy that we got also the amendment approved for another project extension so that we can continue beginning of next year. And everything looks promising that we get the components right on time now. So conclusion out of it, the use of SiC increases the energy efficiency and it enables, especially that's very important, a much more compact design. And that is a big advantage here, besides, of course, the energy savings. And I'm sure that we will get further price reductions with also more components on the market, or the need of the components increases. Okay, thank you very much. Then I will hand over for the next task to Alice Pollock. You're still muted, Alice?
Yes, hello, my name is Alice
Okay.
Pollock, and I will present the outcomes of the tasks 4 in this work package. The task 4 is related to development and validation of new battery module and energy storage unit based on automotive qualified lithium-ion cells. The motivation for this work originates from the Freight Hub project, where diesel electric locomotive with 2 diesel engines was taken. 1 diesel engine was replaced with energy storage unit, and applying reference drive cycle to this configuration yields up to 16% of fuel savings. The chart below just shows the outcomes of the simulation and yields that the necessary energy storage unit would need to store 1.35 megawatt hours of energy and provide 1.76 megawatt of power. In addition to this investigation, some research was performed whether automotive qualified lithium-ion cells can be used for railway applications, purely since they are commercially much more available. Next slide. In this slide, short research was performed on available lithium-ion cells, mainly focusing on different cell formats and different cell chemistries. LFP and NMC chemistries were mainly focused for the further research. Next slide. In deliverable 3 of this task, development and validation of new battery module was performed. The work was performed by our colleagues at CAF. The design consists of design of the connection plates and bus bars for the cells, cooling plates, cell stack with isolation materials, and supervision electronics. The final assembly can be seen in the line below. Next slide. In this slide, the testing of the prototype module is illustrated. The electronics was tested according to the usual standards. The controls was tested in the hill arrangement, and the electrical and thermal performance of the designed module was tested in laboratory. Next slide. In deliverable 4 of this project, AVL was mainly focusing on concept for the complete energy storage unit in order to cover needs from the origin of this work package. Considering the concept of energy storage unit, it turns out that the voltage levels have main impact on the concept itself. The number of modules in the series is significantly impacting the voltage level, while the number of parallel branches is increasing the energy content of the setup. For this consideration, cell module with 100S and 6 parallel cells constitution was considered. The first column of the table below is representing the setup for the highest voltage level, up to 1.8 kilovolt, yielding that up to 4 such modules would be needed in series and 5 of them in parallel branches. The modular concept is visible on the right-hand side, lower picture, and it turned out that such configuration would also be feasible to be installed in the available space inside the locomotive. In further work, the lab scale demonstrator of this setup was built, which is mainly downscaled version representing just single module from this configuration. Next slide, please. Testing of this lab scale demonstrator yields that the requested energy content and the power would be deliverable. Upscaling the results to the complete ECU yields that such energy storage unit would be able to cover the needs of the locomotive. And the last slide, please. So in conclusions, it turned out that automotive qualified lithium-ion cells can be good candidate for the railroad traction battery applications. Collaboration between AVL and CAF PA made possible to manufacture and validate module and to test the ESU demonstrator based on the automotive cells according to the freight hub requirements. And last but not least, this project can lead to a real product which will allow to reduce the emissions of the railway transport, reducing the carbon footprint and improving the energy efficiency of future transportation. There are also some indications for further investigations. First of all, development of high voltage energy storage units remain topic to be further investigated, mainly because the automotive qualified cells are intended for a little bit lower voltage ratings comparing to the railway needs. In second, reliability and efficiency of different lithium-ion cell chemistries for the railroad applications needs to be further discovered. The third one refers to the charging infrastructure for railroad traction applications, which is currently not developed yet. Some hints what would be the possible solutions are listed here. And last but not least, industrialization of the energy storage based on the developed modules needs to be refined. And of course, integration, validation, and homologation of those ESUs in real locomotives needs to be performed. Thank you.
Thanks a lot.
Yeah, thanks, Alice, as well. So do we have any questions?
Are there any questions from the community team? Let's give them a few seconds. Then one question from my side. Are you also going to continue the work in the Europe's Rail program, or is it finished here within Freight Rail 3?
I can answer for the first part. No, definitely not. So we will still observe the silicon carbide. Also now the first samples of 6.5 kilovolt silicon carbide semiconductors will be investigated here. And so, of course, that's very interesting for us to continue. Energy saving is key for the future.
Exactly.
And that can definitely contribute to that.
Yes,
please.
For the second part, I can also confirm that the work will be continued in the Freight Rail 4, mainly in a way of implementation of these solutions in the real locomotives.
Okay. Then no questions in the chat. We have 7 minutes left. Just to summarize a little bit, very interesting results with which we have seen today. I'm not going to repeat everything. I would just like a final remark from my side. If there are any further questions or do you need contact details from dedicated experts, just get in contact with me. I will drop my email address again into the chat. I would also like to thank to everyone which were participating within Freight Rail 3, especially for the last year. There was a lot of work after this global pandemic and that we need to close our work within this project. And I think we could see today that we could really achieve very good results. Also, a big thank you to our project officer, Manuel Alacon, which really supported us within this project, especially when I took over the role from Norbert within the last months. And I would also like then to hand over to Manuel if he wants to say some final remarks to close the session of today.
Of course I want. First of all, thank you very much for your very nice words. I would like to say that I exactly feel the same about you and the work you are doing. I'm extremely happy with how this Freight Rail 3 project is ongoing. We can see after all this time how the different technological demonstrators are reaching its expected level. So I would like to finish today with a couple of takeaways. So first takeaway is that we are close to the end. Freight Rail 3 means that we are very close to Freight Rail 4, but there is some continuation. So basically what we see here will not be drop dead. It will have a continuation in Europe's Rail in the flagship area 5, where in two different work streams, most of the things we are addressed or we have addressed today are going to be continued and further developed. So that's first point. So stay tuned because more interesting things are going to happen in the Europe's Rail joint undertaking within the flagship area 5. Second point I would like to highlight for today is that we still have some journey to go here. So we've got Freight Rail 4, as you all have been introduced in this presentation, where we are going to be able to reach the final maturity level of expected technological demonstrators. So quite eager to reach to that point. We expect that this is going to be around end next year. And so the show goes on, and I see that we are in very good spirits, and we have a fantastic chance, to reach where we're expected. And definitely Freight Rail 4 is going to be a celebration, as we are going to see a lot of very interesting things that are no doubt profiting from the past year's effort of many, many people. No? So these two takeaways: the show goes on in Freight Rail 4, and there is a continuation on the technological demonstrators in flagship area 5. Having said so, I would like to say thank you very much for all of you that have been in this session. We have counted up to 64 different people, so it's quite interesting audience. And of course, if there is any further question, if you feel that you would like to know something more, please do not hesitate getting in touch with us. You can still, in any case, access the Freight Rail 3 project results through the web page. So you can see in the web page all the deliverables and the news, etc., etc. So you can stay tuned with what is happening there. And apart from that, I just want to say that I wish to all of you a very happy season and a fantastic end of the year, and my best wishes for all of you in the next 2020, for the next year, 2023. And having said so, I would like just to say thank you very much, and hope to see you again next year with Freight Rail 4.
Thanks to everyone. Bye.
Bye.